And my pen.
Yeah, I don't understand the definitions.
Greetings and welcome, friends. Today we're talking about determinants and inverses of matrices. But before we get anywhere even close to this stuff, we're going to do some recall problems and talk about the idea of identity and inverse. All right, so identity, this was kind of my best non-mathy definition I could come up with to try to make it a little bit friendly. An identity is a number, all right, when combined with an operation that doesn't change the outcome. So I'll start by recalling here some of the identities for different operations we know.
1 times 1 equals 1.
Yeah. Sure. So let's consider what the additive identity was. All right, additive identity. All right, and the additive identity would be what number, all right, if I have, say, A plus what would equal A? What would go in this box? 0. So the additive identity is 0. Okay? Makes sense. And the identity varies depending on what operation I'm talking about. So that's why I said when combined with an operation. So the additive identity is going to be different than the multiplicative identity. Which, of course, the multiplicative identity would be referring to A times what would equal A. And that's what Jacob just said a moment ago. What was that? Multiplicative identity? 1. So 1 is the the multiplicative identity.
Wait, are you recording this?
Yeah. So the exponentiative identity.
Today's date is the 4th of February.
So exponentiative, that's raising something to an exponent. So A to what power would equal A? Exponentiative, yeah, isn't that a great word? A to what power is A? The 1th power, right? I like it.
Is the identity always 1, or is this just for these examples?
Well, no. Additive identity wasn't 1.
Oh.
Yeah.
Okay.
Yep. So an identity is a number or value when combined with an operation that doesn't change the outcome. All right, so how about inverse? An inverse is a number when combined with an operation that results in the identity for that operation, right, Maddie? So let's talk about the additive inverse. So that would be asking the question, A plus what would equal the identity, and instead of I for identity, I'll write 0, all right? So what would give me back the identity for any number? What would have to go in this box? Negative A, right? So the additive inverse would be the opposite of a number. Opposite. So the multiplicative inverse. That would be A times what would equal the multiplicative identity, which is 1 in this case. All right, so what could I multiply by to give me 1?
1. Oh.
1 over A. And what's a word I could use to describe that? So there's a math word to describe what this is compared to what A is. Reciprocal. Perfect. Right, so a reciprocal is a multiplicative inverse. All right? So exponentiative identity, inverse, that would be A to what power would give me the exponentiative identity, which is 1. So A to what power is 1?
0.
0, yeah. Exactly. So that one's not an opposite or a reciprocal, but that was the zero power property kind of justified that. All right. So these ideas of identities and inverses, I wanted us to consider, think about, prior to jumping in, talking about identity and inverse for matrices. Okay, because that's what we're talking about today. We're going to be able to work with that. So if I'm interested in, say, an additive identity.
We're just gonna jump into it right now.
Yeah. For matrices. All right, so Jacob and Kirsten, if I have some matrix of unknown size, and I want to add something to it, what would give me that same matrix? Yeah.
Additive identity. 0.
Just the number 0?
0, 0, 0.
Oh, so you're describing a matrix that would be the same size, right?
Yeah, and it just
But just all zeros, right? 0, 0, 0, 0, 0, right? Going whatever the size of that matrix is, right? Right, so we describe this as the zero matrix. Right, so that one's not necessarily all that interesting. But multiplication is going to be very interesting to us. Because, I mean, we recall that multiplication for matrices was crazy, right? Abstract, you know, just in general. Let's see if we can figure out what the multiplicative identity is. And for matrices, I guess let me ask this question. Could a 3x2 matrix have an identity? That's an interesting thought. So if I have like a 3x2, don't write this part down just yet. Could I multiply that by something that would give me another 3x2? What size would it have to be? Yeah, it'd have to be a 2x2 matrix, so the inner numbers match, and then the outer numbers would determine this size. However, we actually won't talk about identity matrices that are, you know, dealing with non-square matrices. All right, but I suppose I'd be interested to see if this could even work out. I have a feeling it wouldn't be possible. But let's talk about square matrices specifically. So if I want to multiply a matrix, let's say I have a matrix where its elements are A, B, C, D, and I want to multiply this by some identity, okay? Some unknown identity because we don't know it yet, and I want that to equal A, B, C, D. All right. So first of all, what size would this identity matrix have to be? It'd have to be 2x2 as well, right? I think you guys agree with that. To give me a 2x2. And based on our experience with identities, what do you think we should fill this matrix with? Or what should go on the inside? What should some of its elements be? Yeah, probably, I mean, the multiplicative identity for plain old numbers was 1. Let's consider what this would look like. Don't write this down yet, but if this was all 1s, when I multiply, I'd multiply row by column to get this element here, right? And I would actually have gotten A plus C. So I don't want that plus C there, so what should I do to change that? 1, 0. Let's try that. So 1, 0. So if I multiply this by that, to get this, I would get 1 times A is A, 0 times C is 0. Add those together, I just get A. So that would work out. How about if I multiply it by the second column? I'd get 1 times B plus 0 times D, that's B. Aha, so that works out. Okay, so how about the next row? What do you think should go there?
1 and 0 and 1.
0 and 1?
No, same number, 1, 0 again.
1, 0?
No, 0, 1.
Well, think about this. If it was 1, 0, this would be 1 times A. Yeah, so it's got to be 0, 1. And that works out. Hey, so I think we found it. So it turns out the identity matrix. All right. And when someone refers to the identity matrix, they are referring to the multiplicative identity. But if I refer to I2, I'm referring to the 2 by 2 identity matrix, which is 1, 0, 0, 1. Like so. And yeah, identity matrices, we're just going to be referring to square matrices. Like I said, I'm pretty sure it won't even be possible to get non-square identities. I don't think that would work out. So what do you think I3 would be? The identity matrix for a 3 by 3. What's your suspicion for the top row? 1, 0, 0. Jacob, what do you think about that?
I think subtract, and then it'd be 0, 1, 0, and it'd be 0, 0, 1.
Wow, you guys are I didn't realize, I mean, because I've seen this stuff before. So I mean, I'm trying to present it in a way where hopefully it's intuitive, but I didn't realize it was that intuitive. But yeah, you guys are right. That would just be a diagonal of 1s with 0s everywhere else.
It reminds me of tic-tac-toe.
Sure, yeah. Let's actually just for fun, bam, right there. You like that?
Yeah,
I like that. So if I have I sub n, that would be an n by n matrix, where I'd have 1s going down the diagonal forever, right? And then 0s everywhere else, right? All right. So just so you understand, if you have like a 10 by 10 matrix and you want to know what the identity is for that, that's what the identity would look like. I described this diagonal, by the way. This is my own terminology, but I'll call that the primary diagonal. Sure. So yeah, so 1s are all along the primary diagonal and 0s are everywhere else. Okay? So that's the idea for an identity matrix. Now, I might actually have you guys investigate later whether or not it matters if you multiply on the left or right-hand side of a square matrix. Because, I mean, we know that multiplication hasn't been commutative before for matrices.
It doesn't.
But it's an interesting thought.
I already know it. It doesn't.
Interesting thought. Now, so that's the idea of an identity matrix. Do you guys want an experiment of that, or do you think this is sufficient?
This is sufficient.
Cool. Let's consider this other concept then. Well, the title had multiple parts to it. So we're going to talk about the determinant.
So we have one more thing to do there.
Multiple things. Don't worry about it. Just keep learning. It'll be good. So now I, as an individual who memorizes things based off of their first initial, will definitely call this a discriminant at some point.
Sorry,
What?
I memorize things based on first initial.
oh.
So like, for instance, having Caitlin and Christine in class is not helpful for me.
You're welcome.
Remember last year when you put
Right.
Christiana, Caitlin, Christine, and Kirsten all in the same group?
Yeah, that's just not helpful for me. So I might call this the discriminant sometimes, and that's not what I mean to do. My apologies
Now we yell.
if that is the case. Yep. So, which by the way, just as a side note, what is the discriminant mathematically speaking? Does anyone remember what that's related to? That was related to the quadratic formula. Right, exactly. And that was a way to determine how many and what kinds of answers we'd expected. All right, anyways, let's focus, guys.
I saw graffiti on the side of the building that was a quadratic.
What are we?
All right.
What are we?
We're writing this down. Determinant. Write this down. So let me explain what it is as you guys are writing, and let's minimize these side conversations. Guys. Yeah. So determinant. If I have matrix A, some square matrix like this, here's a 2 by 2, then the determinant of matrix A, which has two ways of symbolizing it. One is by using these kind of, it looks like straight up absolute value bars, which is actually somewhat not helpful. I wish it had its own symbol. You might also see it written out DET as a function of A, where A is a matrix that you'd be inputting into that function. You might also see the entire matrix written with absolute value bars.
How come it's in a different order?
Yeah.
Oh.
Oh, I wrote. Oops.
Oh man, good catch, Hank
Oh, is it supposed to
Sweeney.
be A, B, C, D?
Oh yeah, yeah.
Okay, I was like, I wrote A, B, C, D.
Look at-
Oh, man.
Good save, good save.
The C is still incorrect.
Yeah.
Oh, you're just gonna make it into a.
Oh right, I have to erase the C as well. How did that happen?
Okay.
There we go. Good move, everyone.
That was
Crazy.
sucky for me.
Whoa, Jacob, inappropriate language recorded on the internet. Thank you, friend.
Wait, you don't find that as a swear?
Thank you, friend. So, anyways, so here's the determinant. One thing that I want to point out is that notice these absolute value bars, so to speak, can go around the actual elements of the matrix. Okay? So that's why something as subtle as these little horizontal pieces to those brackets, if those are lacking, it's something entirely different.
Excuse me.
All right?
Would the
Christine, what's up? Why are you talking right now?
Would the A, would it be AD minus BC now, or just be AB minus CD, or is that right?
Nope, this was correct. Yeah. And the way that I derive this, by the way, is you multiply the diagonal, A times D comes there, and C times B, or B times C, because multiplication of numbers is commutative. Right. Yeah, don't worry, we're going to do an example of this, don't worry.
Wait, so the A with the kind of absolute value thing, that's the same thing as the determinant of A, which is the
Here,
same
Christine,
thing.
quiet please. Kirsten, be quiet please. Willow, be quiet please. Caitlin, question, yes?
Okay, the A with the absolute value kind of things, that's the same thing as the determinant of A, that's the same
Yep.
thing as the, okay, so it's all different ways
All
of
of
writing
them,
it?
yeah, you got it, you got it. So I could do the determinant of the name of the matrix, the determinant of the elements of the matrix, or I could use that notation itself. So it's the product of the primary, right? I multiply the primary diagonal, and I subtract the product of the secondary diagonal is what I'd refer to that as. All right, so let's actually do an example of this, just so we can see what this looks like.
Is there any kind of official definition of what the determinant is, like in words, or is that complicated?
The actual, well, I guess we'll do some more work with it in a minute. It's used. Why is everyone talking? I don't understand.
Is it pause now?
It's kind of rude.
Is it pause?
No, it's just you guys are rude. That's all. And now the internet knows you're rude. That's pretty
It
terrible.
all goes back to Hank doing the sound.
So, the determinant itself, what I want to point out, will not equal a matrix. The determinant itself, if I do AD minus BC, that's just going to equal some number. All right? And so that number will, in a moment, actually relate it to the area of a parallelogram. So think about that number as just being like, if I asked about the area of a square or something like that. All right? So it's a number that represents something to do with a matrix. We'll incorporate it later on in calculating inverses in just a moment. So it's going to end up being a piece of a formula, but it also has some other uses and indicators for us, which is nice. So let's do an example of this.
Yeah, I don't get what you just said at all.
Yeah, exactly, and that's fine. That's why we do an example.
Estimation, do you think this takes like a little bit of page, like
I've still got at least another page left.
No,
So
this a lot of pages.
example?
this is gonna be like one row. This will be fine. So find the determinant of this 2 by 2 matrix. So what do? I multiply the primary diagonal. So I would have -1 times 4. And I subtract the product of the secondary diagonal. Right, -3 times 2. All right, this is always subtract. Okay? So -1 times 4, I guess I'll work down here, is -4 minus 6, and I get a determinant of -10. All right, and like I said, it's just a number. All right, just
That's all you have to do for that?
a number. Yeah, for that particular problem. Eventually, we're going to put that into more use.
So when you're subtracting secondary diagonal, you always have to go from bottom up.
Well, it doesn't matter. You could do 2 times 3.
You need to minus 3.
What?
You subtract.
Yeah, this subtraction sign is always the same in the formula. Yeah, 2 and 3 and 3 and 2 multiplied be the same thing. So you can switch.
It doesn't.
What's your question, Willow? Could you clarify?
No, never mind. Just waiting for something.
Okay. No, the different, right, I'm subtracting the product of the secondary diagonal, yeah.
Question.
Yeah, Caitlin?
Not that it matters in this problem because both B and C are like positive integers, but
Yeah, if this ends up being negative, yeah, double negatives or triple negatives, you're going to have to take all of that into account.
yeah, but it should be like it should be B times C, and that's
Yeah, it doesn't matter which way you do that. Yeah, it's commutative to multiply.
okay.
So, in the case of regular numbers, not in the case of matrices, but in the case of numbers. So let's fit another little example in here.
I think we got this part down.
Well, this is, don't worry, I've chosen my examples for a good reason, Jacob. There's a reason for this. So let's multiply this. So primary diagonal is 3 times 4, and I'm subtracting the product of the secondary diagonal. All right, negative 2 times negative 6. So that's going to equal 12. And let's see, am I adding or subtracting here?
Adding.
Negative times a negative is a positive, and then there's one minus sign still left over. So I'm subtracting 12, and I get equals 0. So the determinant for this problem is 0. And a special note about determinants that are 0 is this. Note. Important note. Any matrix whose determinant is 0 has no inverse. Intriguing. So not all matrices are inversible.
Who's inverse mean?
Inverse is, in the case of multiplication, the thing I would multiply it by that would give me back the identity. All right, and that's why I wanted to do the recall on the identity and inverse, just because, like I said, I memorize things off first initial, so inverse and identity, you could definitely see me mixing those up. No, don't worry. There's a whole other concept we're learning after this. We've got like 3 more examples. Don't fret, don't fret. It's going to be great. So let's do the determinant of a 3 by 3 matrix. And the book actually teaches this a different way, but I'm going to teach you a way that I think makes a lot more sense and is also scalable to 4 by 4, 5 by 5. Not that we'll ever end up really doing those. But this is the idea. All right, so here's a 3 by 3. I know I'm calculating a determinant because these are kind of absolute value bars and not the regular square brackets, so to speak. And in order to do this, this is our process. I'm going to rewrite the first 2 columns on the right side of this. Okay? And I'm going to try to maintain the same spacing. So I'll write 2, 1. I'll write 3 and negative 3. I'll write 7 and 1. Don't worry, there's a reason for it. Don't worry. No, the first 2 columns. That's what I said. First 2 columns, right? Bless you. So I copy the first 2 columns on the right-hand side with the same spacing here, so to speak. And the concept is going to generally be the same. When calculating the determinant of a 2 by 2, I found the product of the primary diagonal and subtracted the product of the secondary diagonal. It turns out in this case, I'm going to find the product of 3 primary diagonals. All right, so this is going to come from 2 times negative 3 times 9. Okay, so that's what? Negative 6 times 9 is negative 54, I believe. All right, another primary diagonal. 1 times 5 times 7 is 35. And another primary diagonal, 4 times 3 times 1 is 12.
1 times 5. Oh.
Right?
This is terrible.
Yeah, really.
Don't worry, it's actually not that bad. Just keep following along and it's going to make perfect sense. And once I have these, I just simply, I'm going to add these together. And I get negative 7 in this case. So that is the sum of the products of the primary diagonals. And what do you think I'm going to do next? Multiply the secondary diagonals. That's fine. You guys learned how to multiply matrices. This is just a little bit of a unique process, but you'll be able to figure it out. Yeah. So 7 times negative 3 is negative 21, times 4 is negative 84, I believe. And notice this is why that spacing was kind of important, just so my little diagonals would line up kind of nice. 1 times 5 times 2 is 10. And then 9 times 3 times 1 is 27. And I'm going to add those together. So let's see. And I get negative 47. All right. Now, what did I do with my products on the 2 by 2? I subtracted them, right? So I'm going to do exactly the same thing here. I'm going to take the product of the primary diagonals, right? And you get
threes on the end.
what 3s?
Like the threes, the negative threes,
And
all the way at the end.
the 2 that you didn't do anything with.
Yeah.
This guy?
The negative 3 and the
This 3 ended up over here, so it did end up working,
Oh, yeah.
right? Yeah.
And the
So-
negative 3.
Well, this negative 3 was included in that. Or this negative 3? Yeah, I guess this one didn't end up being as important. Yeah, you're right. Because it was already incorporated right here and
How do
here.
people find this stuff? Like, let's just do this.
Yeah, mathematicians discover different things over time. Yeah,
Like, what's the reason?
you should look it up. Maybe I'll make that a side quest. So I'm going to take the primary diagonal, subtract the secondary diagonal. So that's going to become plus 47, and I find that the determinant is 40.
Wait, you subtract the 2?
Yep, secondary from the primary.
The secondary is 1 or 3.
Yeah, yeah. Yeah, if you want, you could write that, you know, there and there.
A negative minus a negative is positive.
Yep, accurate. So that's a determinant for 3 by 3. We won't be finding inverses of 3 by 3s by hand, which is fortunate. But it's still good for you to see this because it still can have this property still applies, and we've got to know how to do that too. So let me show you this interesting process here. This is called, we're going to find the area of a parallelogram.
Is this the third concept?
Nope,
No.
this is still related to determinants.
But I've already used 3
Oh.
Well, I mean, like front side, back side, and front side.
Yep, we're still going. Using absolute values of determinants.
Damn.
Stop complaining so much, guys. I am your math teacher. We're learning math that has been deemed valuable by all the states, so to speak, or what, 46 of them was it?
Not Texas.
Not
Oh.
Texas.
Don't they make our calculators like Texas Instruments?
I think they're made in Taiwan or China at this point, but. So find the area of a parallelogram using absolute values and determinants. So let me show you what I mean by this. If I set up a parallelogram in a particular little arrangement,
Should we copy this down?
you could draw a quick little sketch. You don't necessarily need the grid here. So if I set up kind of one of my coordinates, one of my vertices of my parallelogram at the origin, I just want to point out that this is A units over, right, and B units up, which in this case B is 0, right? So here's the point AB for one of the corners. And this point is C units up, right, and D units over. Right, so there's the point CD. And then this third point, if it's going to be a parallelogram, is actually going to be predefined by its location. There's no other option for it other than this arrangement. So A plus C, predestination. Actually, I just realized, wait a minute. I think this is supposed to be A plus D. Look at it. Yeah, aha. Check this out. A here. And, oh, guys, that's what I messed up. Watch this. Bam. This was D units up. Silly me. I mixed up my X and Y's. Hey, it happens to all of us. Happens to all of us. I wouldn't even go to say that I'm the best. So, yeah, well, I avoided it. So, yeah, here we go. So, this distance, the X coordinate of this point, notice, is A units over, and this additional distance is C. So this overall horizontal distance is A plus C, and that's why this coordinate is A plus C. Right? Well, check this out. This little triangle over here is the same as this little triangle over here. It's C units across, C units across. Whole distance would be A plus C, so A plus C. Right? So, yeah, this is related to matrices, just you wait. Now, if I had a value of B that was not 0, so if this point ended up being up or something, it still would work out, where I would just have a parallelogram kind of like that. But this overall vertical distance is going to be the value of B plus the value of D to give me that overall vertical component. Okay, so it turns out if I have a parallelogram arranged in this format, that I can actually find the area by taking the absolute value of the determinant of this matrix. And to point this out, I just want to indicate that AB, notice, are one of our points here, and CD is this point up here. Right? So I just kind of arrange it in that order. If I find the determinant and then take its absolute value, because the determinant can be negative, all right, as we saw with negative 10 showing up as one of our answers earlier, we do end up, being able to take the absolute value of that, so it's positive. Since area hopefully would be a positive number, as I'm sure you guys would agree. So, all right, we're doing good. We got this. We got this. So let's do a little example of this. So find the area of a parallelogram with vertices at the following. So in order to do this, the trick is I've got to figure out what my matrix is. What is my A, B, and CD? And the way I realize this, well, I know A, B, C, D aren't going to be the 0, 0, right? So it's going to be one of these guys, or two of those three, rather. And the trick is realizing that this third point, this x-coordinate was the sum of the other two x-coordinates, and this y-coordinate was the sum of the other two y-coordinates. So for this set, which of these points have an x-coordinate that is the sum of the other two's x-coordinates? Right, notice 3 is equal to 1 plus 2. Right, and notice 9 is equal to 5 plus 4. So the ones that I'm going to exclude will be this guy, and this will be my AB and CD. because 3 was equal to 2 plus 1, and because 9 was equal to 4 plus 5. So I can now plug those in, and I'll have 2, 4, and 1, 5. So here's my matrix. I want to find the determinant of it, right? So the determinant of 2, 4, 1, 5. Let's see, that looked too much like 15 there. That's going to equal, well, how do I find the determinant? Multiply the primary diagonal. It's 10. And I'm going to subtract the product of the secondary diagonal, which is 4. And I get 6. Which, this says I have to absolute value it, right? Recall that? Absolute value. But 6 is already positive, so I'm good. So this is 6 units squared, would be the area of that parallelogram.
We just put those, whatever the whole thing just because. I don't know that. How would we know that?
Well, I was, like I said, I was able to determine which points I was going to use as A, B, C, and D. I knew I wasn't going to use the origin. And I was able to determine that this was the point opposite the origin because its coordinates were the sum of the other two.
Why is that one right there?
This
That
one? This picture?
No, the 2, 4, 1, 5 is not doing anything.
Well, I was just indicating that this is the matrix, and now I'm finding the determinant of it. You don't have to write it twice, don't
Can we
worry.
go back to how we x'd out the 0, 0, and 3, 9?
Yep.
It shows 24, 2, 4, 1, 5. How did we get there?
Because
Yeah, because the coordinate that I wasn't interested in, all right, was this x coordinate is the sum of the other two x coordinates, and this y coordinate was the sum of the other two y coordinates. All right, so that's why 3, 9 I didn't use because of that
But
reason.
we only would be able to figure that out if it had the image of the parallelogram.
No, because notice 3 is equal to 2 plus 1,
Oh.
and 9 is equal to 4 plus 5.
Fair enough.
All right. So that means that the area of this parallelogram is 6 square units. All right, which previously finding this would have resulted in all sorts of weird, gross square roots in calculating it because our previous area formula for a parallelogram. Do you guys know the area of a parallelogram formula?
no.
It's actually nice, base times height. But the problem with this is my base would have been at some weird angle. Like if I called this my base, then this is my height. Right? And I don't know this distance. I mean, you could do it. It just would have been a pain. So I just want to point this out that you can use determinants in this technique. But the main reason we'll be using determinants is to calculate the inverse of a 2 by 2 matrix. And I'm guessing this is why I had my little typo earlier. Rearranging my A's, B's, C's, and D's. So, if my original matrix is A, B, C, D, then A inverse is how you would read this. Okay, this is read as A inverse. I guess that arrow is not very helpful, is it? So read as A inverse. And you might remember the -1 exponent representing inverses before, when we did inverse functions back in the day. Also, recall that the multiplicative inverse was the reciprocal. And notice a to the -1, according to our properties of exponents, actually would equal 1 over a. Oddly enough. So that just is classic inverse notation. So now look at this formula. So I multiply by a scalar, which is 1 over, what does the absolute value bars mean again? 1 over the determinant. So that's just some number, right? Just like how I'd gotten the determinant to be like -10 earlier or something like that. Yeah. So whatever the determinant is, that becomes the denominator of this little fraction. And I multiply by the matrix, and how is this matrix different than this one? Well, let me show you.
Negatives up and down.
The primary diagonal was switched, and the secondary diagonal was opposited. I like that green and purple. It reminds me of classic Joker colors right there. So last example, let's show you how to find the inverse of something.
This is the last one of everything?
Yeah.
The last example.
Last thing for today, yeah.
Oh,
Don't worry. Don't worry. So, if I want to find the inverse of this, the first thing I would need to find is the determinant of this matrix. So how do I find the determinant? By multiplying the diagonals. 2 times 4 is 8, right? Minus this product of the secondary diagonal. 4 times -3 is -12. And if I subtract those, well, it's actually becoming adding. So that's going to be 20, right? So that means A inverse is going to be 1/20 multiplied by the following matrix. So for the primary diagonal, what do? I'm going to switch the 2 and the 4. So now it's 4 here and 2 there. And on the secondary diagonal, I opposite it. So it's going to be a -4 and a +3. So I would accept this as an answer, but you also could multiply through by the scalar, which usually means fractions. But most of the time there's not necessarily any benefit for that, especially in what we'll be doing anyway. But I could distribute 1/20 by all of these. So 4 over 20 reduces to 1/5. Then I'd have 3/20. Then I'd have -1/5. And I'd have 1/10.
We don't see it.
Right. But the reason I'm writing it out here is I do want to point out that the inverse is another matrix. Now, question. Let's see if you guys get the general macro concept. If I multiply this by that, what should I get?
Well, say it again.
Should be your original, right?
If I do A times A inverse, what should I get?
A.
One.
0.
The 2 by 2 identity matrix is what I should get. And I could actually use that as a check if I wanted to. But today's lesson's been long enough. I think we're good. So, thanks for watching, Internet friends. That's all about determinants, identities, and inverses, blah, blah, blah.